A wave is a disturbance that moves along or beneath the sea's surface and can be described by wave height, amplitude, wavelength, and wave period. The energy from the sun heats up the Earth inconsistently. This means that the sun's energy does not heat up the Earth's poles and equator evenly. The Earth will constantly try to counteract the difference in temperature by trying to even out the Earth's surface temperature. This makes the air move around in quasi-regular circulation patterns. These patterns are called statistical highs and statistical lows. 51% of the Earth's energy gets absorbed into the land. The rest gets sent back out into the atmosphere, hence heating at the Earth's equator, which makes the heat rise. The equator heats up first, then the poles. Warm air rises, travelling north and south because of Coriolis force. The air heats up and cools down, which creates high and low pressure systems. These pressure systems is what creates wind. The direction of the wind is affected by Coriolis force. Coriolis is the reason why everything in the northern hemisphere turns right and everything in the southern hemisphere turns left. This is also the reason why lows, highs, ocean currents and tides move like they do. Convection is the movement which moves heat from one part of the system to the other, normally in a vertical direction. Once again, the sun heats up the land at different rates. This creates weather systems. As land heats up, the air molecules become less dense over the land, making them rise. As they rise is where the sea breeze comes in, which is called convection. If the wind was blowing down on the water, it would create depression in the water's surface. This would make a lump of water appear that has been displaced and moved to the side. When the wind stops, this will then cause the depression to spring up and then back down. The waves will continue to grow as the wind blows across the surface of the water. As the sea gets rougher, the wind is able to grip onto it a lot easier. This means that the waves get bigger. The bigger the waves there are, the more wind is able to grip onto them, meaning that they will grow at a much quicker rate. The anatomy of a wave consists of a few things. Amplitude, which is the vertical movement of the water from its still position. Height, which is the distance from the trough of the wave to the crest. Frequency, which is the number of waves that pass a fixed point within a time interval. The frequency, which is measured in hertz, is the number of waves that pass a fixed point per second. Wave period is the time between any part of the wave. This could be from the crest or the trough. When a wave passes a fixed point and the wave after it passes the period. Wavelength is the distance between any part of the wave and that of the wave after it, which is basically the horizontal distance between the beginning and the end of the wave. The moving bodies of energy till they hit the shore. This energy flows in a circular motion under the water and is known as oscillation. To work out the group speed of a wave, you first have to find the individual wave speed, which is done by using the equation velocity equals distance divided by time. Group speed is half that of the individual wave. Waves travel slower in shallow water because the orbitals cause friction when they touch the seabed. This friction slows down the waves. These then begin to refract to match the coast. When waves are travelling over shallow water, they slow down and build up height. The topography of the seafloor is never the same, meaning the angles of refraction change all the time. If a wave hits an obstacle such as a headland or harbour wall, part of this hits a shadow zone. This contributes to the wave and scatters it. This is known as diffraction. As the water depth becomes shallower, the orbital motion of water molecules below the surface of the waves reach seabed, which slows down the waves. These are known as orbitals. This equation can be used for all waves, but can be simplified for deep and shallow water waves. Waves travelling in water deeper than one half of the wavelength is known as a deep water wave. The speed of the wave is the same to their wavelength or wave period, and this is the equation to work it out. Waves in water shallower than 1/20th are shallow water waves. They hit the sea bottom, which makes their speed slow down, and you can use this equation. We are now going to look at an example of how to do a wave equation. For example, if a wave was travelling in water 30 metres deep and it had a wavelength of 120 metres, you'd use the wave equation to calculate speed in metres per second. And this is how you'd do it. Gravity is always equal to 9.8 metres per second squared. We already know the depth and the wavelength, and pi is always 3.142. This equation is for an intermediate wave. They have a ratio of depth wavelength between 1/20th and 1/2 the wavelengths, and does have complicated transitional characteristics that are a function of both wavelength and water depth. Waves break on a beach with more of a gradual slope. The top of the wave, known as a crest, spills down the face of the wave. These waves can be relatively slow and are best suited for beginner surfers. Surging waves tend to form on a very steep beach and do not hold a lot of energy. They are flat and low and they move smoothly up the beach. It can happen at high tide when the slope of the beach is steep and the waves are unable to break properly. Plunging waves form the classic barrel or tube. The wave travels from deep water to shallow water very quickly and has to reduce its speed rapidly, and these are the waves that surfers tend to look for. Length will also affect the type of wave that breaks on the beach. The longer the wavelength, the waves will move more quickly and will arrive in shallow water before they start to break. This means that the waves will be steeper and faster. It also affects the type of breaker. Offshore wind creates the best waves. It blows against the wave and postpones the top from breaking. This makes the wave break later. Onshore wind has the opposite effect. It pushes the top of the wave. This makes them messy and break earlier than usual. Slopes also affect the type of breaker. Gentle slip causes the wave to drag along the bottom. This makes the top of the wave overtake the bottom earlier than it should, which makes the wave break in deeper water. The wave shouldn't be too steep and the crest should crumble down the face. A wave on a beach with a steeper slope approaches the beach at greater speed. A rapid change creates a higher and steeper wave. The top of the wave quickly overtakes the bottom, and this can make a steeper and hollower wave. Eventually the wave will break and disperses into the sand through sound, vibration, friction and heat, and this is the end of the wave.